for the introduction and invitation to share our work with you all today. We're delighted to be here at Penn State. And we're going to jump right in with a kind of brief background on how we operate through research and practice, and share some past work before delving into logs and lumber. Our work is developed through two venues, After Architecture and the Before Building Laboratory. Both venues foreground material investigations from conventional construction to maturing digital tools. After Architecture is our architecture practice named to convey the built environment's impact on cultures and ecologies. We implement ideas and systems developed in the lab on real-world projects, including temporary installations, as well as permanent buildings and public art. Our work is characterized by a foregrounding of material and its accompanying narratives. We started our practice through designing and building permanent works of public art, which often doubled as furniture and lighting. Early on, we also pursued design build competitions. As our work developed, we found that our firsthand experiences with construction stirred up questions around material processing, impact, and efficiency. Such questions are explored through the design across scales, from an outdoor classroom to a theatrical landscape. And these questions also inform the design of housing that leverages thermal mass and existing rooms. More recent work seeks to collaborate with natural materials and processes, including the cultivation of barley seeds in shaped molds that produce both models and furniture. Here, the overall form is controlled by the designer, while aesthetic effects of the surface, texture, and density are co-authored with other living organisms that have their own specific behaviors and growth patterns relative to light and gravity. As a complement to our professional practice, we co-direct an academic research laboratory at the University of Virginia. The Before Building Laboratory pioneers new material assemblies to advance circular construction practices, allowing for experimentation and the taking of risks through grant-funded projects that are often not possible in purely client-driven work. As the climate crisis leads to indeterminate material supply chains, architects and builders must look beyond existing industrial materials for construction. There are numerous materials to be found locally that, if strategically sourced, have the possibility to improve native ecosystems. For this goal, we collaborate with a team of student research assistants to investigate the use of native grasses, invasive plant species, and trees targeted by invasive insects. In each case, we work to understand and leverage the unique properties of these atypical natural materials. We develop carbon sequestering material assemblies, engaging maturing technologies and inventing and building new tools that enable us to work with natural materials in new ways. Research projects often begin with material samples and prototypes, some of which are seen here. And it is important to us that every research project matures into an inevitable assembly that can link a specific material approach with its unique spatial opportunities and experiences. Some examples of this approach include the development of a custom pneumatic forming machine, which is deployed in the construction of a series of biomaterial panels. So the kind of machine on the left is answered by the assembly on the right, where panels that combine kudzu, bamboo, pine needles, and several invasive plant species are formed into these panels that are flat on one side and curved on the other side, and installed as a kind of ruin or topiary hedge at the Knoxville Museum of Art. One of the kind of goals here was to reposition the aesthetics of digital fabrication, replacing the smooth, crisp machine tectonic synonymous with the digital turn with something fuzzy, furry, or shaggy. In another project, Mass Grass, we develop applications for the common, abundant, and rapidly renewable grass family as a material which grows in various species globally, and with which nearly the entire plant can be utilized. In this case, we're using bundling strategies, which build on kind of global vernacular building traditions, and allow for the overlapping of material to create a kind of continuous network of members. Beyond our own investigations in bio-based materials, we seek to create venues for this work and build community of scholars by raising funds for curating and convening events. Such public facing endeavors aim to bring new sustainable construction methods into popular discourse. So to this end, we curated the biomaterial building exposition in 2022. And one of these projects may look familiar. The event built on UVA's academical village legacy as an architectural testing ground. The exposition expanded on this tradition, forging a path towards a radical material future. And then in addition to a series of 5 installations, a gallery show brought together work from UVA and across the country to frame a larger field. So 5 architect teams were invited from other American universities to exhibit projects on UVA's grounds, which resulted in a series of full-scale installations, which start to speculate on the kind of spatial implications of these new material assemblies.
So to transition and talk about logs and lumber now, our recent work focuses specifically on wood, where the work is questioning the planar assumptions of mass-produced lumber by interrogating the practices of sawmilling. How do we turn logs into lumber? To frame this work, we wanted to start by sharing our current favorite image. This is a late 18th century engraving of a sawmill. We find it to be delightfully absurd. So to break it down a little bit, this is from a document that's an account from the American Revolution. It's by a British officer who was traveling on foot from Montreal to Virginia, documenting kind of what was seen in America. And the sawmill depicted in this image is located in upstate New York. It rests in the shadow of wispy trees that appear taller than clouds behind them. A solitary figure within the sawmill structure is in the sawmill structure. The structure itself appears to be vomiting. I can't put this. If anybody has a better word, let us know. But the sawmill appears to be vomiting milled lumber into the still water of the creek below. This now industrially processed material disappears below the mysteriously still surface of the water and miraculously emerges perfectly stacked in orthogonal piles on the entire process is overseen and is the leisurely viewing of both soldiers and toga-clad onlookers who casually lounge in classical repose. Questionably, logs are nearly absent from the image. Besides 1 or 2 linear elements on the hillside, we see only the standing trees and then the lumber that results. This transformation of the natural bounty of America into mass-produced goods in the form of standardized lumber is represented as being at once immense, effortless, and also picturesque. So we're kind of obsessed with this image. So we'll begin then by looking at and talking through 2 ways to straighten a log through human and embodied intelligence. Since industrialization, the answer of how to straighten a log has been largely to subtract, to transform the raw arcing forms of trunks and branches, which balance their search for light, water, and structural integrity into a simple orthogonal prism, to break wood down and reassemble it into a uniform and predictable element, producing substantial waste and requiring a lot of energy in the production of what is still essentially a raw material in the form of dimensional lumber. So through this process, we argue that the intelligence of the grown material is somewhat lost. It trades greater embodied energy and waste for ease of construction on site. There's perhaps no building quite so easy and cheap as a humble 2x4, which is optimized not for material economy or intelligence, but for human labor. This design of the building unit expands to encompass an entire range of building construction practices and products. There's this whole ecosystem that shapes our built environment, determines everything down to the size of the pickup truck. These standardization practices were embraced by modern architects. In 1931, The Dwelling of Our Time was an exhibition by Lily Reich and Mies van der Rohe that displayed full-scale prototype homes, seen on the left, surrounded by, on this mezzanine, by displays of the materials and products from which the houses were made. So they were constructing an overt association between the industrial materials and modern design. And this was an attempt to package this kind of new material ecosystem through industrialization, specifically for a public audience, to convey those ideas for the public, this relationship between material processing and the production of architecture. Even as new movements in architecture have embraced bespoke form, prisms and sheets remain the basic unit from which geometry emerges. The tectonics of the digital turn extend and reapply effective methods to now create custom form from standardized materials. So in projects like these, we have logs that are turned into standardized sheets, such as plywood, and subsequently then turned into bespoke customized forms through digital fabrication processes. And in each step in that process, there's energy and time and often wasted material. So most recently, the timber turn in architecture has resulted in a series of products that thicken and multiply the familiar lumber unit and plywood sheet into meatier assemblies that promise larger buildings and more sequestered carbon. So this is an argument made for more material rather than less, right? The more wood you can put into a structure, the more carbon you can sequester within that structure. But these are similarly bound by the formal restrictions of dimensional lumber, and they largely are a kind of ecosystem of building products that produce straight beams and columns and flat floors and walls. So one approach that we're interested in as an alternative to straightening a log can be found in the piece on the left called Reframing Nature. This is by artist architect Alan Wexler, in which a small arcing kind of the natural geometry of a branch is the starting condition. There are small incisions made along the trunk of the length of that branch, and small wooden wedges are slipped into that mass, redirecting the center line of the tree into a straight path. So those wedges are precisely placed around the circumference of the branch, and their width is specific in relationship to the geometry of the branch at that moment in order to straighten it. We also consider the work of Andy Goldsworthy, whose wandering line of logs, seen on the right, leverages the curvature of those logs and begins to address this question of straightness or texturing of the material. So Andy Goldsworthy intuitively systematizes theorems and phenomena in his work in service of a singular artistic vision, and this becomes a kind of collaboration between the designer, design intent, and found grown form. So to get into some projects now, tangential timber, which you might notice from the posters in your beautiful school here. This project pilots an application for cross sections of wood. These are called either rounds or cookies in the timber industry. I wish we thought of this name, we did not, but we love that they're called cookies. And for the project, we sourced wood from a campus stockpile of trees that are felled by storm, disease, and infection. And this material was either too short, too curved, or otherwise irregular to be turned into conventional lumber. So we were looking for other applications for this material. Working with this regular natural material, we consider a sentiment captured in Mario Carpo's observation that scanning as a process is already widespread within the forestry industry, for example. It allows for timber members to be maximized in the production of standardized lumber. And the ubiquity of scanning within this industry makes both the technology and the industry as a whole, or makes the technology readily transferable to form searching methods. So Carpo writes that, quote, "The only way to deal with the inherent capriciousness of living materials is to react to their whims and volitions on the spot and on the fly." If traditional project delivery involves the creation of design documents long before material is ever acquired, twinning instead offers the potential to leverage 3D imaging technologies to inventory material inputs, allowing for the design process to progress as a dialogue with materials. There's a feedback formed between the specific material that you're using and how the design itself takes shape. Twinning presents one strategy for incorporating material feedback, referring to the creation of digital doppelgangers of physical artifacts through 2D and 3D imaging technologies. The technology itself is not new. It's been around for quite a while, actually, but it's becoming increasingly accessible and available to more people. Shown here is an example of early digitization practices in Frank Gehry's office. So here they're deploying a 3D pantograph in which points are located in three-dimensional space on a physical object, in this case, a large-scale architectural model. And those points are then translated into the construction of a 3D digital image. So in this project, the material sourcing began with about 56 linear feet of logs that were cut on a traditional bandsaw sawmill seen here into 164 cookies. Each of the cookies varied in thickness from about 3 to 5 inches thick, and each one was totally unique in geometry just based on the material. We weren't selecting for any particular shape or geometry or size of cookie. In this case, we were just taking whatever was available with a stockpile of material that we started with. Standard 3D scanning methods of each cookie would have produced really detailed digital models that would promptly crash our computer if we're working with all of these in the same file in Rhino and Grasshopper. So instead, we developed a custom low-cost, low-data workflow to document each piece of material. This process involved taking a single photograph. Here you see 2 of the photographs taken for 2 of the cookies. We took a single photograph of each cookie surrounded by a series of physical registration dots that are those black markers in the 4 corners, and a T-shaped registration mark drawn onto the material itself that's used to track the orientation of that material. These photographs were then processed in Grasshopper to correctly scale them, to correct for perspectival distortion when the photo was taken, to trace the 2D profiles of the material, and to extrude them into simplified digital twins. This process distills the information gathered to minimize file size and focus on the most relevant information. So we're editing out all the extra detail that we don't necessarily need for this particular application. The script then sorts the digital cookies across a compression shell structure. So this is sort of a masonry approach. The cookies are sorted by diameter and thickness, with larger cookies on the outside or bottom of the structure and smaller ones are in the middle or top of the shell. We did a spring simulation to gather the cookies here, and on the right, you see them in their kind of aggregated form with the overlaps, the controlled distance of the overlaps being important for the generation of joinery between the pieces. The vault is a square in plan with arched openings on each side. To fabricate the structure, the first step was done with a 5-axis CNC water jet. This was used to cut the complex joinery in each cookie with a series of ruled surfaces. Right, so we had to cut all the way through the material. There are limitations in all these tools. We view them as opportunities. In this case, we have to cut all the way through the material in a straight line, hence the ruled surfaces. This joinery was tailored to and actually generated in part by the profiles of each cookie itself. So there was a lofting of each cookie edge profile from top to bottom. The images you see here are the front and back of the same test joint. So you can see how there's an interlocking geometry visible on one side. On the left, the cookies appear shingled on the right, and that geometry of each cookie informs the kind of location of each of those edges on top and bottom. Finally, timber units double as both structure and ornament. Structural stress lines are inscribed into the surface of the vault and produce a CNC milled texture. Right, so this is a more kind of traditional digital fabrication process, but with custom toolpaths generated from our scripts. And these lines double as a graphic pattern for aligning the wood masonry units in this kind of 3D puzzle. This also registers as a second wood grain overlaid across the tree's growth rings. And we also use this as an opportunity to control this thickness of the shell. So the depth of that cut was determined by the density of these stress lines from a structural simulation, and the shell was thicker where there were more forces present and thinner where less material was needed. So the pieces, once being fabricated, are relatively easily assembled by 1 or 2 people with minimal scaffolding, and the structure quickly becomes self-supporting. Those lines are really helpful to actually assemble this thing. So you have this 3D puzzle that you're trying to figure out, and those lines, those kind of graphics on the surface became a kind of visual aid in that process. The interior of the structure takes on an entirely different texture than the exterior. The vaulted design is a small-scale investigation that suggests how customization technologies can enable designers and builders to work more closely with and responsively to irregular natural materials across scales.
So in the next series of projects, we're looking at, again, how to respond to the specific geometry of material. Surfacing roundwood was a workshop we led at the University of Texas at Austin, which explores possibilities for roundwood timber through low data 3D scanning methods and the robotic sawing of roundwood logs. In this case, we make use of smartphone photogrammetry apps to 3D scan input material. In this texture map image, you can see the T-shaped registration mark again on the upper left that is used to track orientation of both the digital model and the physical material throughout design and fabrication. The workshop builds on other researchers' work mounting custom bandsaws to robotic arms as end effectors. Rather than build a bandsaw from scratch, we mounted a small off-the-shelf woodworking bandsaw on a robotic arm. And then using the 3D scans, we generated tool paths relative to the curvature of each log specimen. These cut logs were assembled into a columnar assembly with a straight conventional base and a capital that embraced the deformation of each log's center line. Our work with water jet methods on tangential timber and robotic arm methods on surfacing roundwood brought to the surface the drawbacks of each. With both energy intensive machining requires a kind of expensive fixed in place tool, as well as specialist software knowledge. And so in response, we endeavored to build a deployable, lower cost and more accessible counterpart to these tools. Our custom computer numerically controlled sawmill advances the traditional analog gas-powered sawmill with sensors, motors, and guides choreographed by G-code. In a traditional bandsaw sawmill, blade height is controlled by manual winch and horizontal movement is accomplished by an operator physically pushing the bandsaw along material. In the new machine, all movements are achieved by electric motors and CNC control. Horizontal movement is accomplished by chain drive, while vertical movement is accomplished by ball screw drive. New blade guides enable angling and twisting of the bandsaw blade while cutting, and the machine is fully electric, can be powered by a small portable generator if you're taking it off-site where electricity is not available. Like the maturing of CAD software during the early digital turn, we believe the accessibility of our techniques will influence adoption. And so anecdotally, we have found that kind of builders, facilities personnel, the public is maybe more eager to engage with the familiar tool of the sawmill than the robotic arm, which maybe enables a much wider variety of operations, but is thought to be relegated to kind of industrial factories. And so this kind of precipitates a hypothesis that such a tool may allow for wider engagement. And so once we had this kind of tool online, the first project that we constructed was Sylvan Scrapple, which was an installation for Exhibit Columbus, a biennial exhibition that takes place in Columbus, Indiana, and curated by the Landmark Columbus Foundation. Exhibit Columbus is somewhat unique among biennials in its commitment to facilitating sustained engagement between the designer and the city in the year of project design with multiple public presentations and stakeholder sessions. The biennial, situated around a compact walkable downtown, Columbus has an amazing and unique architectural legacy with a collection of over 80 significant works of architecture. But despite this rich history, Columbus faces challenges activating its downtown, particularly post-pandemic, adapting the grand scale of its mid-century urban space design to fit its population of 50,000, and then building sustainably, which are really kind of a series of issues that many cities face. Our project is sited along the Avenue of the Architects, in between IMP's Cleo Rogers Memorial Library and the Kevin Roche Columbus Visitor Center, and down the block, the historic Queen Anne style Erlin, and in late 2022. So Sylvan's grapple responds to these kind of specific site conditions with transferable tactics, urban activation, mass timber construction, and material reuse. A 110-foot long snaking wood wall was inserted into a 2,000 square foot landscape plan, framing a series of elevated seating areas and overlooks. The project combines two material streams, landscaping waste and demolition material, to form a wood wall and gabion furniture. Curved logs were cut into 3-inch wide curving boards and stacked into walls. And the project leverages curvature in plan to create thin structural walls with a series of arc sizes that allow for the nesting of geometries during the sawmilling process. The curved mass timber walls are designed to avoid toxic adhesives and allow for easy assembly and disassembly by hand. Stacked boards are post-tensioned with threaded rods, eliminating the need for glue and allowing for disassembly. Integrated springs permit fluctuations in moisture content in the untreated wood, which over the course of the year can produce height changes of up to 2 inches. The resulting walls are very solid but extremely thin, with porosity created by the bark surfaces of the milled logs. And then a second material system collects bricks salvaged from the Irwin block, which had burned down, and a building across the street, which was being renovated, the First Christian Church by Eliel Saarinen. And it takes the bricks from these two buildings that were, not going to be used again, and collects them in a series of custom gabion cages that augment the existing brick planter wall. The gabion cages are complemented by a dining table formed with bio-based resin, which collects construction scraps and kind of anchors the installation with a story about material sourcing and reuse. And after the exhibit's maybe short lifespan, as part of the biennial, these pieces become permanent furniture, pieces that can be used elsewhere offsite. With that table, the public was kind of invited into a game of I Spy, where they could locate panels from Saarinen's tower across the street, fallen branches from the nearby park, bricks from the burned building. The snaking wall invited visitors up into the planter, framed thresholds, and provided serene nook. And some of our opportunities to interface with the public provided key takeaways for us as designers, which was that really kind of material reuse became especially resonant when residents can point to the nearby site from which the material was sourced. In the next demonstration, we again used the CNC sawmill, this time adding complexity to the cuts that we're able to achieve through the production of crinkle cuts. The tool is used to cut wavy or sinusoidal boards, which are kind of serial nested non-planar lumber units that can aggregate into lightweight forest wood panels. This workflow produces two types of crinkle cut elements: uniform boards, which are rough cut on all 4 sides, which are 2 inches by 2 inches in cross section, and live edge boards, which are rough cut on all 3 sides, leaving one live edge 2 inches thick with a variable width along the natural geometry of the log. And so here you see the kind of regular unit which is cut on 4 sides, and then the kind of irregular unit which has one raw side. To mill this material, a series of wiggling tool paths are cut on the sawmill, producing undulating live edge slabs. These slabs are then rotated 90 degrees and cut again. The resulting wavy or crinkle cut boards join with fasteners into lightweight porous structural wood panels and are deployed at an inhabitable scale through a demonstration assembly, which was rapidly assembled by hand. The pavilion was assembled in a single day as part of a workshop at New Jersey Institute of Technology. Orthogonal door and window openings are located on opposite corners of the installation, placed so that there are only 3 lengths of panels. And this kind of optimized our input log lengths. Finally, the pavilion uses beetle kill ash logs gathered from the forest floor. Beetle kill ash is identified by the curving path of the invasive emerald ash borer, which tattoos these markings into the cambium layer or living tissue located below the bark. So the beetle kill path markings remain visible on the live edge units, pairing strikingly with the wiggly geometries of each crinkle cut. In this way, the live edge crinkle cuts bridge industrial seriality with material expression. The markings of a pest transform into an efficient structural geometry, serially manufactured for lightweight panelized timber construction.
So building on these projects and this technology that we developed, we're now working with students to explore the formal potentials that result from cutting non-planar lumber. This is an example from a workshop we taught together at Syracuse University last fall, in which students worked through 2 projects. The first was the design and fabrication of a small expanded timber volume, just so happened to function as a stool, and a much larger series of surfaces that they built collectively to form a much larger collective table. The first project asked students to work with the geometry possible with this technology to expand 4x4 lumber into an expanded forest volume using a series of cuts that are analogous to what's possible in the sawmill. And so students in this case were working with analog tools, bandsaw in their woodshop and starting with rectilinear material, but they were encouraged to experiment with different cut geometries in both plan and section, and then explore how the resulting 3-dimensional forms could be aggregated into these larger volumes and think about the kind of spaces formed within them and effects of surface and density and texture. In this one example, this is a project by a student, Fu Chuang at Syracuse. A series of cuts are made in 2 directions that end up producing both a lot of individual units and units with some complex geometries that still can be nested in a variety of ways. The second part of the workshop asked students then, based on what they learned from this first exercise, to join into teams of 4 and design a table using only a single log that would be cut on the robotic sawmill. So we taught students how to use this tool. They were taught how to go with this workflow from a Rhino model, generating cutting planes to produce G-code with custom Grasshopper scripts. And Katie and I then used that G-code to mill material for them in Virginia before bringing it up to Syracuse for them to assemble their projects. Each group received a single log worth of material. It was about 5.5 feet long. And they didn't see this material ahead of time. They knew the kind of approximate size of it, but there was a kind of unknowability in the material that would be produced, and they had to reconcile with that through the assembly of these pieces. So the first thing we asked students to do upon receiving their milled material in person was to reassemble the milled elements of the log that got kind of mixed up through fabrication and transportation. This turned out to be a surprisingly productive exercise. You had to kind of read the complexities of bark and grain and geometry to figure out how these pieces were nested together. And once those pieces were nested on the left, students were able to kind of then deconstruct the log and rearrange it into the predetermined aggregations that they had developed digitally. In some cases, that went exactly as planned, and they were very pleased. In other cases, there were either challenges with the actual irregularity of the material in aggregating their designed forms, or they found other opportunities in the material and wanted to kind of accentuate or celebrate different qualities of the grain and the bark and the geometry of the material that was produced. And so there are a variety of strategies that came out through that actual physical process, right? When we do things digitally and physically, there's always unknowns and realities that we have to deal with physical material. And this was a really nice way of kind of working through those issues. So much of our work advancing bio-based materials in construction takes form as material prototypes and pavilions. These small-scale investigations and temporary installations can sometimes feel free from the constraints of permanent construction and habitation. They're kind of like parlor tricks. So for a recent exhibition, we developed a series of living rooms and parlor tricks that are a series of models in which we try to translate some of these material strategies, construction methods, types into domestic tableaus. And so in these models, for example, curving wood walls draw from sylvan scrapple to frame a sunken courtyard within a living space. A scrapple floor embeds offcuts into the home's plinth and garden. Or cookies from the wood masonry compression shell, tangential timber, and nonlinear wood column surfacing roundwood might merge together in a model into one cohesive system, becoming a living room with a vaulted wood masonry roof. It's also kind of challenging, and the exercise of actually producing these models at a larger scale was kind of a lesson in and of itself. And we were really interested in how the combination of the kind of horizontal and vertical surface then produced these kind of seamless transitions and unexpected geometries as the raw form of the logs or sticks at model scale is cut into the kind of designed architectural space. So through full-scale and habitable prototypes and speculative models, we're interested in this new spatial and experiential opportunities of these material strategies. In this project, Sheets and Slabs, we present a set of twin vessels. They're identical in form, but differing in material construction. And they're designed as testing chambers for neurological research on the effects of architectural materials on human stress levels and brain activity. So material composition is the primary focus of the project. The goal was to compare a drywall interior space to a more bespoke wood space. Here you see one of the student study participants wearing the mobile EEG headset in both of the two spaces during the testing process. The volumes are the design of the spaces themselves, taper from rectilinear bases into funneled skylights. Material is subtracted from each volume to form an entry threshold at the corner and compress an entry condition that then releases vertically to make the space feel larger and less claustrophobic, even though it's very relatively small in plan. And the spaces were constructed as panelized assemblies. So it's all made as kind of like flat sheet assemblies that were then bolted together on site. You could transport them, fabricate them somewhere, move them to the space where we were doing the testing, bolt them together, and then later on detach those panels and move them to their future location. The control sheets is clad in drywall on both the interior and exterior, while its doppelganger slabs scribes live edge slabs into meandering fields of grains and curves. After data collection is complete, the chambers will be repurposed as study rooms on campus.
So as we finish up, we'll transition to some of our professional practice work. Located in Northwest Washington, D.C., the Camp Barker Memorial responds to the landscape of American monuments, taking form as a series of spatial markers which convey a complex history. The memorial was designed and commissioned in early 2017 and completed in 2019, a period when the role of Civil War monuments was being reconsidered. The Camp Barker Memorial answers the brief for the design of 3 entry gateways to an elementary school by framing and revealing the site's history as a Civil War era contraband camp. A typology specific to the Civil War, the contraband camp came into being as a Union establishment where people sought refuge from Southern enslavement. In the aftermath of the war, the site gave birth to a longstanding community just blocks from the heart of the Capitol. Theorist Adrian Parr notes that at their best, memorials avoid monumentalizing the past, choosing instead to tension the past with the present while joyfully looking to the future. The Camp Barker Memorial attempts to take on Parr's charge, responding to the object-centered urbanism of the Capitol by shaping the memorial as a series of thresholds integrated into the fenced perimeter of a public elementary school. The site, which encompasses an entire urban block, is bounded by the linear school building to the north, while fencing on the east, west, and south encloses the school grounds, which double as a public park. The memorial portals address the history of the site and its recreational grounds, intervening in each of the 3 fenced elevations. The goal is to take the monument off its pedestal and put it at eye level, physically and visually accessible to the public, a series of thresholds that visitors must pass through to access the grounds. In contrast to the marble monuments that define Washington, D.C. The exterior surfaces of each portal are clad in charred wood, a finishing technique which offers fortification against UV, fire, and insects and other environmental agents. Standing within the portal and looking into the brass liner, one can see the outline of one's own reflection and the surrounding colors, a kind of visible ghost that registers a shared human condition. Integrated into this palette are a series of narrative bas-relief sculptures by artist Vinnie Bagwell, which convey the site's themes. The recessed sculptures, cast of black and bronze to match the wood, are set into the thickness of the folding portals. A continuous folded plane forms the floor, walls, and roof. On the playground side, smaller side wings create habitable spaces that engage the scale of the school child. The Camp Barker Memorial germinates the site's contradictions for emotional impact. The memorial beacons the elementary school, abstract space frames narrative sculpture, and finally, charred wood folds over a thin brass liner. We'll end by suggesting applications for the woodwork through Hearth Cabin, an ongoing design build project cited in Vermont's scenic Champlain Valley. The project distills the components of the classic backwoods cabin down to a wood stove and stack of logs, hybridizing these elements into a seamless occupiable space, a domestic chimney. Contrasting the vertical timbers of the surrounding woodlands, the building takes form as a horizontal layering of lumber, from its slatted facade to the logs it stows. An open joint rain screen sheathes the building, enveloping walls, roof, and chimney. Stocked with firewood that doubles as fuel and ornament, the cabin is equipped for cold nights. And so the exterior is completed, and from the CNC cordwood system is underway. And so born from the woodlands, the cabin is built of and fueled by surrounding timber. In closing, we propose advancing the adoption of sustainable construction by playing off the familiar and pragmatic. We've found that the public warmly welcomes variations on wood construction as a familiar material whose performance can continue to be enhanced, promising scalable solutions. Carbon sequestering, renewable, well codified, and used in building applications globally, timber offers a short runway to broad adoption. And recent developments in mass timber enable the construction of tall, resilient structures. That said, there is much work to be done. And so a key focus is to identify the spatial potentials of these new systems. And as well to develop the tools for working with this material. So our current work aims to bridge academic research to industry practice. And we find that new tools allow us to question the default geometries that have been available to us since the Industrial Revolution, which enables a new spatial paradigm. So we'll end by asking you to join us in welcoming the timber turn in architecture. Thank you. We're happy to take any questions.
It's amazing work, and I think you could be here. I'm amazed at how you're able to do all that you're able to do, fixing band saws to robots and all this kind of stuff. I'm just thinking about practically how to get a lot of the stuff done that you're doing. And then the work is amazing too. What are some of the lessons, like, I was picturing myself building the pavilion that you're showing on your poster. And we have these precise digital tools that allow us to do all these things, and then you're using these methods that are that become ways outside of those tools to actually track what you're going to do. But then I picture myself actually building it and running into all sorts of problems. And I was wondering if you did run into all sorts of problems when you went to build it, or if it just kind of fit together perfectly. Like, I don't know if it, like, did you dry fit it and it didn't quite work, and you had to hand cut stuff? How much was analog after the digital process took place?
I think it's a great question. I'd love to say it all fit together perfectly. But I think the reality is oftentimes with metal fabrication or robotic construction, there's a lot of human fabrication and human construction in the workflow. And so one of the unique challenges of wood is its tendency to shrink and warp, and it's not homogeneous and it's not still. So that was definitely something that caused a little bit of need for trimming when we assembled. But it's also something that's informed how we've been thinking about more scalable solutions. I think tangential timber represents like a very bespoke application that would require maybe a lot of time and energy. So some of the things we're considering is how do we make units that perform better but are actually more predictable, easier to anticipate those kind of challenges.
Yeah, I think I totally agree about that being maybe farther on the like bespoke end of the spectrum versus something like the crinkle cuts, like undulating timber, in which the individual elements have a degree of standardization, right? So it's much more predictable kind of how those will be. Something else that's kind of at play in I think almost all of these projects is that we're kind of doing these things for the first time in each of these applications, right? And so while we have some kind of I don't know, opportunities provided by these not being largely client-driven work, right? We can take risks and kind of fail if that's warranted and can inform the next thing, which is really productive. But there's also kind of timelines relative to those grants. And so in the case of tangential timber, we actually had to kind of document that material. We took those photographs and digitized the material very early in the process, very soon after those pieces were cut. And while we were developing the kind of aggregation fabrication strategies for that material, it was like kind of sitting there drying, and we tested some methods for like preserving it and coating it. Right? The cookies are particularly bad because the end grain just kind of wicks all the moisture like a bundle of straws out of the material, and they develop cracks. But most of the kind of treatment methods that we tested would include like impregnating the material with additional chemicals that we weren't a fan of thinking about, like what happens to this thing at the end of the lifespan. And so in that case, I think there were some challenges caused by the shrinking of that material based on like what we had scanned versus what it was when we kind of came to cut the geometry and put the material together. And in the future, I think if we plan that process out, kind of properly cut the material into cookies, dry it ahead of time, right? Like timber seasoning is a whole kind of art and science in itself. I think that would alleviate something, like that's something we would do differently in the future in that particular project. But I think with everything, we always find that we often think of these digital processes as being like hyper precise and super accurate. In many cases they are, but there's always like the hand in assembly of these things, right? The like analog is always present as much as you may try to get away from it.
And I think that to me, that's great. The Columbus example to me was where both examples, where the irregularity and the lack of precision with how things go together is actually a great part of the aesthetic. It's a beautiful thing. It's interesting to think about this line that you walk between enclosure that keeps the elements out and not losing that spirit of the thing that doesn't quite fit is actually a beautiful part of it.
Yeah, it's like a question of tolerance in all of these projects. So we're trying to design systems now that can like accommodate that range of tolerance, especially with like a living material that's changing over time or changing seasonally.
So along those lines, there's a product called Superwood that's been developed by Tang Li and Hangbing Liu at the University of Maryland, where they're compressing the wood, making it a lot stronger and potentially less deformable, subject to shrinking. So have you adapted that to any of your projects?
Sure. Yeah, it's a great question. So yeah, I've looked a little bit into that. It's like super impressive what they're doing. I've also seen a lot of other like, timber treatment methods. It's a process they developed in Europe. It's like acetylization. Might be getting that terminology wrong. They basically like sort of like pickling your timber, right? And so you like treat it with these kind of vinegar and other solutions. And it produces kind of like material that can withstand the elements much better on like facade applications, for example. So we find all of those products to be and strategies to be like super exciting. Our work right now, I think, is focused more on kind of raw or untreated timber. We're trying to think about, especially with these like temporary installations, what happens to that material after its lifespan, right? And so there's questions, I think, of both like energy and other materials that like go into the production of certain timber products. But also what happens to them upon decommissioning, right? I think ideally we'd have everything last indefinitely, right? You sequester all that carbon within buildings, and hopefully our buildings will get to have longer lifespans, or they should. But there are inevitably questions of like what happens to that material at the end of its life, right? So yeah, I think we're really excited by those techniques, and I'd love to get my hands on some of that material and see what's possible with it. I think the like kind of properties of how you can actually work with and cut and mill that material would also be really different and present other exciting opportunities. Yeah. Good.
Yeah, thank you. Thank you for the talk. It's amazing. I had a question about the design study that you did, like between the wood, the non-wood spaces, because I'd like to know more a little bit about it. Because yes, there is material, but there is obviously the shape of that space and the light indirect. In the space that you designed. So yeah.
Yes, that project was driven, I think the design of the spaces themselves is driven by the need for like semi-enclosure, not being able to see outside. So we were trying to make spaces that were like pretty small, but you wouldn't have the people feel claustrophobic, so that wouldn't influence the reading, the testing too much. So we ended up going with light coming from above so that it wouldn't feel claustrophobic, but that it would feel, but that it could still be quite small and you wouldn't have outside views affecting the data. But it was an interesting process because we were collaborating with neuroscientists and environmental psychologists. And yeah, the iterations kind of went back and forth with, the things they wanted to control, but also the things they wanted to avoid. So to have it be like a completely neutral box actually had like raised other concerns for them, kind of shapes the development of their project. Interestingly, we did find late in the process that the psychologists, two of the neuroscientists, they all had done undergrad in architecture before pursuing these other fields. So we thought that was interesting that to come from that background and then the desire to study real habitable space, whereas a lot of the testing in this area is actually done through like visualizations, kind of like video game style environments rather than the physical environment. Yeah.
So you kind of touched on this after question one, but I guess wood as a material is fairly unidirectional and kind of like fibrous. And it seems like with a lot of these forms, you're kind of working counterintuitively against that, particularly with like the cookie vault. I'm wondering kind of what challenges you've run into working like that and how you've overcome this material like breaking or maybe not being in the direction it wants to be.
Yeah, that's a really good question. And it's something that we're like kind of working through right now. So a lot of like these are kind of, we see them as like demonstration pavilions. We want to get to kind of inhabitable space, kind of full scale. You can be in the space first. It's larger than a kind of like tabletop experiment or a beam or a column maybe. But in these initial examples, like there was a lot of distortion cookies in particular, in like crinkle cuts, for example, or Sylvan Scrapple. There wasn't really distortion or cracking in the material as it dried to cause significant problems. In the case of Sylvan Scrapple, we were anticipating that, and that's why we had that die spring detail to account for like the height of the wall changing in the taller walls by up to almost 2 inches annually is what we calculated. But I think as we move forward, we're working now on designing and then hopefully this summer fabricating a series of kind of like structural panel assemblies. We want to kind of think about how do we take some of these more bespoke strategies and think about them in a semi-standardized way, like how could this provide and maybe a more porous or more lightweight or more material efficient alternative to CLT, for example. And in those cases, I think there's a lot of structural testing we're going to have to do, particularly in response to your question about like disrupting the like continuity of that grain, right? So I anticipate there might be some challenges there. We don't have data on that yet, but we're planning for it as much as we can, or anticipating that that will be the case. On the other hand, I think there's a lot of like aesthetic opportunities in it actually, because when you take these like non-planar tool paths and cut in and out of the material, you kind of get these amazing kind of green patterns that are kind of unlike anything I've seen in milled lumber before, right? The like standards of like plain sawn and rift sawn, quarter sawn, are like totally almost out the window when you introduce these other kind of dimensions. And so I think there's a lot of exciting aesthetic opportunities in it at the very least. Yeah, in the back.
So thank you for showing the work. Very interesting. I was wondering about the wood itself and how the selection of the wood comes into play. There's some, there's elements in the work that you showed that I'm thinking of Scrapple, for example, where you're taking waste product or interrupting demolition, let's say. The mobility of the technology you're using seems like it could be really compatible with the kind of climate change that's happening with wood species in the region that you work in, say Virginia to Vermont. I'm thinking of like Eastern hemlock and black walnut. Being selective with the wood might allow you to anticipate some of the wood change. Both of those species have different behaviors when you're drying them, when you're cutting them, when you're doing woodworking. Are you thinking about specific woods to apply? And even for example, you go to Home Depot, there are certain boards that just can't be bought because they're so twisted. But your system would allow you to work with twisted wood in a way that actually takes advantage of the twist. Can you talk a little bit about the wood, I guess, that you're interested in?
Well, I guess one thing I'll say is that one of the key ways that we source wood is through a group at our university called UVA Sawmilling, which doesn't actually run a sawmill, but serves as a kind of intermediary between facilities and the architecture school, where trees that come down for construction or because of storm or disease are kind of collected into a stockpile. And so that's made a really amazing material resource for us individually as researchers, but also for our students. Like they can get wood very cheaply. And if you hire a sawyer for a day, it might be like $150 or something, and you could produce, thousands of dollars of wood. So that's been a kind of interesting pipeline where we're working with wood that happens to be available because of these projects. But I think as the research has developed, species selection has become, something that's driving the behavior, right, and driving the constraints of the project. So, for example, with tangential timber, we had all these different types of wood, and some did really well. Some you couldn't even CNC. Traditionally they just kind of like explode when you tried to do basic like CNC routing on them. So this species selection has become a increasing focus. We've been thinking about it a little bit from the side of like the ash borer creating this like material inventory. But I think thinking about the wood's qualities is also an area of increasing need of focus.
Yeah, I think a lot of our species selection up until this point has been based on just like what's readily available to us in our community, working with UVA Sawmilling. So in some cases, the like ash borer, right, produces this huge stockpile of material, then ash becomes a primary material for that project. I really like your reading of like the ability of the tool, enabling a kind of like migration relative to where this new species are becoming available, or there's like an opportunity space to use that material. It's kind of like thinking about, the explosion of like mass timber and like bipartisan support in the Pacific Northwest, now kind of feeding like the emergence of new like timber manufacturers and like standards being developed specifically around southern yellow pine and like the Southeast, right? And I think that's the next like big market for like engineered lumber and mass timber. But I think there are other opportunities potentially enabled by this tool. We were thinking about it as like one of its advantages over like robotic arm systems, where you have to get like a foundation cast, like our school had to get a new foundation when they put in their robotic arms, like get the precision that was required by the manufacturer. Whereas we can just hook this up to a truck and tow it wherever it needs to go. We've also are thinking about potentially other species that could be usable because of how we can work with like non-linear material, exactly like you're saying. So for instance, thinking about the relationship between like invasive insects and tree species, so everybody's heard of the spotted lanternfly. I don't know if you have, probably seen a lot of it. So it's migrating like along our interstates, like we're getting it in Virginia now, and it's projected to cause like tens of millions of dollars in agricultural damage in the next decade or so. And the primary host tree is Ailanthus, commonly called tree of heaven, and this is itself an invasive tree that's like aiding and facilitating the spread of this insect through the southeast. And that tree produces some really interesting material, but because of the kind of its formal tendencies, it's not really conducive to like milling it straight lumber. You end up with a lot of like smaller twisting branches and things. And so we're thinking if we introduce digitizing processes, we might be able to actually make use of that material because we can now process non-planar material. And so we're definitely interested in like, we have a couple ideas of specific species and applications, but I think just rethinking like what's available or how we think about the sourcing of the material is something that's becoming increasingly important in our work, even though we started becoming opportunistic about kind of just using what was at hand.
Thank you.
Yeah.
The question also maybe gets to the like vast opportunity space here, right? There, like, you can take species that want to warp, you can focus on an invasive species, you can focus on the tool. So yeah, the mass timber market currently has like 8 products, but I think there's a lot more that we can contribute as architects. So and just getting involved, I encourage it.
Part of the reason I asked is because there are several people in the room here who we took a field trip to George Nakashima and saw his wood pile. And it was just amazing to hear his daughter comment that when he started making all this live edge stuff, it was in the garbage pile, you know? And you guys are at that point also where you have the option to use stuff that no one else wants. And it's got its own rules in a way, but you've adopted the technology to follow those rules. So I think it's an interesting area to explore, is that idea of species and the kind of remnants of all of this catastrophe that's happening in wood.
I don't know if anybody's meandered through Lowe's or Home Depot recently. They recently started selling live edge slabs for close to $100 last time I saw. That if you look at it, there is like a bark edge on it, but it's actually like, you know, composited of boards put together. So it's like an engineered product, but that's like somehow made desirable by it being live edge. And so I think there's like a cultural moment too of like this interest in that like natural expression of that material. Yes.
Your work. It's a different version of the previous question. So you showed these 2 paradigms at the beginning of your talk. One, for the 15th century engraving, whatever you put in at one end, the same thing comes out the other. And then you showed the Andy Goldsworthy and Alan Wexler pieces where it's like extreme careful attention to the individual piece of wood, its materiality, its shape, its thickness, and everything. And your work is somewhere in that spectrum. I want to hear, I mean, I have my own guesses, but I wanted to hear where you're pushing in that spectrum. What's really of interest? The formal interest really is forefronted in the way that you're working on it. So one could say you're working like the sawmill, but you're changing the sawmill. Do you see yourself working at the other end of it also?
Really good question. I think that's something that's put much more articulately, but something that we've kind of been thinking about for a while. I mean, I'll start by saying one of the reasons that we like show other biomaterial experiments in the beginning and then like transition specifically to timber is because at some point we decided that we wanted to strategize ways to like potentially have this research like have impact in practice, right? And so there's like so many barriers to a lot of these new materials that there's just going to be some time delay in how like new codes and standards are developed to accept that into our like super, I don't know, bureaucratic, like the logistics of like building construction. And so with that, like we focused on timber, but then there's this range of like the kind of tangential timber, the cookie shell on like the far bespoke end, and then maybe the latter projects on the more kind of like semi-standardized end. We're definitely interested in material expression, and part of that comes from a desire to minimize waste in the production, right? And so normally when you mill a log into lumber, you first cant it, you cut it into kind of the largest rectilinear box that will fit within that log, and that produces these offcuts or scabs that are like just sort of like the barky pieces that go into the waste pile. And that quickly, when you do a day of milling, like is this massive amount of volume of material that we're interested in finding the use for. So how can we allow that variability to come into play? And so this like desire to then like start to veer back towards standardization comes up against like the challenges of the material. And I think one of the solutions that we're interested in is how do we now like design these assemblies in a way that they can inherently account for that variability of the material, right? So like, how can we make kind of the most use of that material? How can we have the greatest yield in the material and have that expression of the natural quality of the material, but in an assembly that still will have like some kind of knowable performance, or have basically a kind of tolerance range that's designed into the aggregation that allows that variability to happen.
I like the way you described the question. I like the way that you described the etching as like anything you put in comes out the same. Yeah, I think as architects, we're constantly like pulled by these two different things, right? Like the art, the expression, like the beauty, the singular thing, and then, well, how can we actually make an impact? Or like, why does our work matter? How does it serve someone besides ourselves? You know, so I think that's some different forces that we wrestle with, and I'm glad that both those forces are there. So I think being somewhere in the middle is where we are, and keep keep being. But you know, I think something that was interesting about doing the crinkle cut one was I think we can do a lot more than just that, but it doesn't look when you look at those parts, they don't look efficient in any way, but actually they're nested together within a log. So there's a kind of efficiency to them, even though they look inefficient. And I'm interested in that tension between, you know, like what looks actually quite individual, but maybe actually results from something quite optimized. Or so there's something there, but I appreciate the question.
One last question.
Thank you very much for the presentation. It was really incredible work. I just wanted to ask, when you made that transition to the CNC sawmill from the CNC robot arm, you mentioned briefly that there might have been, you felt like you might have lost something in terms of the design freedoms. Could you expand a little bit more, if more on that, and maybe whether or not you ran into occasions when you were fabricating pieces where you were thinking, oh, well, if we had the robot arm, we could have done it in this more dramatic way. Were there any moments like that?
Yeah, I think what's interesting to us is to understand the constraints of a tool. So working with the water jet, you know, the water jet is cutting with a straight strand of aggregate, right? And so it's means you can only cut things with a straight line. You can cut curves, but it's got to be made up of straight lines, right? And so thinking about that as a design constraint, it's productive in tangential timber. There were other ways we were interested in overlapping the cookies that just wouldn't be possible with the cutting capabilities of the water jet. When I think about, you know, the kind of constraints of the robotic arm versus the robotic sawmill, the robotic arm maybe has you can have a different range of motion. The sawmill is kind of along a track, right? So there's something linear about it. The robotic arm can do many different things. And so I think we don't want to minimize what the robotic arm can do. It can do many, many things. But we're kind of interested in something that's maybe more deployable, tailored to work. So we're thinking, you know, the bandsaw mounted on the robotic arm maybe isn't the best solution for wood, because you can't go into the forest and cut things, or there's an accessibility challenge where you need to be a certain scale to buy into a robotic arm system. And you need a certain amount of specialized knowledge. So all to say, there are maybe more capabilities in some regards to a robotic arm, but are they the right capabilities for the impact that we hope to have? Maybe that comes back to the previous question, like the whole goal with the democratized tool is more people can access it, right? If we make a great end effector, maybe fewer people can access that. So the sawmill in a way becomes like more easy to implement at scale than the crinkle cuts right away. But there's kind of different ways I think we're trying to have impact.
So much.